Welcome to the deep dive, where we really try to get under the hood of complex ideas. If you're fascinated by numbers, especially if you're getting into number theory, you've probably bumped into the OEIS, the online Encyclopedia of Integer Sequences. It's just this incredible resource, isn't it? Full of patterns, connections, things you just wouldn't expect.
Oh, absolutely. It's like a huge interconnected library of numerical ideas, sequences that sometimes link math areas you wouldn't think are related, or even, connect out to science. It really speaks to how interconnected things can be.
Yeah, that interconnectedness is exactly what we love exploring here. So today, for you listening, maybe you're a student, maybe just curious, we're diving into one specific sequence, OEIS A000263, and the name itself, well, makes you stop and think. Number of partitions into non-integral powers. What on earth does that mean? How do mathematicians count something like that?
Right, and that's our mission today, basically. To unpack A000263, we'll look at its precise definition, how you might actually compute it, and a bit about where it came from. And we're sticking just to the OEIS entry itself, showing how much information is packed in there.
Okay, let's get started then. A000263, you might see old codes for it, like M2967 or N1200. That shows how things get cataloged over time. It kicks off with these terms, 314, 39, 91, 173, 307, 502. It really takes off quite quickly.
It does. The list goes on, 779, 1150, 1651, and so on, all the way up past 170,000 for the terms listed.
And there's that note, offset 31. What's that telling us?
Yes, important detail. It means the first term listed, the 3, is actually A3. So the sequence index n starts at 3, not 1 or 0 like some others, so A3 is 3, A4 is 14, and so on. It's just a convention, but you need to know it to match the numbers to the definition properly.
Right, makes sense. A3 is 3, A4 is 14.
Got it. So the big question: partitions into non-integral powers. Let's break down that definition from the OEIS comments section.
Yeah.
It says, AN counts the solutions to the inequality by 112 plus by 212 equals n for any two distinct integers, 1 equals by 1 by 2.
Okay, let's unpack that piece by piece. Non-integral powers here specifically means the 12 power, square roots.
So not x squared, but square root of x.
Exactly. And notice it's an inequality. We're looking for pairs of numbers by 1 and by 2, where the sum of their square roots is less than or equal to n, not strictly equal to n. That's key.
Less than or equal to n. Okay. And what about the by 1 and by 2 themselves?
Right, they have constraints. They have to be integers. They have to be distinct, so by 1 can't be the same as by 2. And they're ordered. 1 must be less than or equal to by 1, which just must be strictly less than by 2. So by 1 is always the smaller positive integer.
Distinct ordered positive integers.
And an is simply, well, it's the total count. How many pairs by 1 by 2 satisfy all those conditions for a given value of n?
Can we maybe walk through the first one, A3? How does that work out?
Yeah.
Good idea. So for N3, the inequality is square die 1 plus square die 2 with 3. We need one way with 1 by 2. Let's try the smallest possible by 1, which is 1.
Okay, everyone.
So square die 1 plus square die 2 was 3. That's 1 plus square die 2.
Right. All right.
Subtract 1 from both sides. Square die 2 was 2.
Right.
Square both sides by 2 equals 4. Now remember the conditions. By 2 must be an integer, and by 2 must be strictly greater than by 1, which is 1.
So by 2 could be 2, 3, or 4.
Exactly. That gives us 3 pairs, 1, 2, 1, 3, and 1, 4.
Okay. That's 3 solutions. What if we try by 1 equals 2?
Good question. If I1 equals 2, the inequality is square die 2 plus square die 2 is about, what, 1.414?
Yeah, roughly.
So 1.414 plus square die 2 equals 3. That means square die 2 must be less than or equal to 3, 1.414, which is about 1.586.
Okay.
If we square 1.586, we get roughly 2.515. So by 2 must be less than or equal to 2.515. But we also need by 2 to be an integer greater than by 1 equals 2.
Are there any integers between 2 and 2.515?
Nope, none at all. So no solutions when I1 were 2. And if you tried by 1 equals 3, square root 3 is already about 1.732, leaving even less room for square root 2. So you definitely won't find an integer by 2 greater than 3.
So the only solutions for NR3 came from by 1, and there are exactly 3 of them.
Precisely. Which matches a 3-3.
That makes it much clearer. Okay, so we see how it's defined, how those first terms come about, but calculating a 100 or 1,000 by hand like that seems tedious.
Oh, incredibly tedious. Impractical, really. And that's where computation comes in, and why the OEIS often includes code.
Right. It mentions Maple and Mathematica code here. How does that work, generally speaking?
Well, without getting lost in the exact syntax, the basic logic in both is pretty similar. They iterate through possible values for by 1. Usually they'd loop by 1 from 1 up to maybe n2, y n2. Because if a by 1 was bigger than n2, then square by would already be bigger than n, making the inequality impossible to satisfy since square 2 is positive.
Okay, that makes sense as an upper limit for by 1.
Then, for each by 1, the code figures out the maximum possible value for by 2. It rearranges the inequality. It
Okay.
covers 2 n's 2 by 1. So x2 equals n equals what's by 1. So a2 equals n squared by 1, 2. Let's call this maximum possible value max 2.
Got it. Calculate a max by 2 based on n and the current by 1.
Exactly. But n2 also has to be an integer, and it has to be greater than my 1. So the code uses things like the floor function that just takes the integer part, rounding down. It ensures by 2 is an integer, and checks that the largest possible integer by 2, which is floor max by 2, is actually greater than or equal to by 1 plus 1, since by 2 by 1.
Floor function, right, to get the integer part.
And then comes the clever counting part. There's often a line like a plus floor max by 2 by 1 or something similar.
Floor max by 2 by 1, how does that count the solutions?
Let's think back to n3 and by 1, 1. We found the maximum by 2 is 4. So floor max by 2 by 1 becomes floor 4, 1, which is floor 3, which is 3.
And we found 3 solutions, 1, 2, 1, 3, 1, 4. It worked.
Yes. What that floor max 2 by 1 calculation does is effectively count all the integers k such that I1 k equals max 2. In our example, it counted k2, 3, 4. It's a really efficient way to sum up all the valid by 2 values for that specific by 1 in one go.
Wow, that's neat. A compact bit of code to do all that counting.
It is. And the entry credits R.J. Mathar from 2009 and Jean-François Alcover from 2016 for these implementations. It shows the collaborative building on each other aspect of the OEIS community, too.
Absolutely. Okay, definition, computation.
Yeah.
What about the history? Where did this sequence come from?
Well, the entry itself was submitted by N.J. Sloan, Neil Sloan, the founder of the whole OEIS project.
The man himself.
Indeed. His Handbook of Integer Sequences from 1973 and then the Encyclopedia of Integer Sequences with Simon Plouffe in 1995 were the precursors to the online database. Monumental work. And A000263 is listed in those original books. M2967 was its number in the 1973 Handbook. I mean, as you think about how much work went into finding and cataloging these before the internet and easy computation.
Definitely gives you some perspective. And there's a reference here that looks, well, really interesting. A paper.
Yes. This is, I think, quite fascinating. It points to a paper by B.K. Agarwala and F.C. Aulick. The title is Statistical Mechanics and Partitions into Non-Integral Powers of Integers, published way back in 1951 in the Proceedings of the Cambridge Philosophical Society.
Statistical mechanics. How does that connect to counting pairs of square roots?
It's one of those beautiful, unexpected connections. It suggests that this mathematical structure, counting solutions to this specific type of inequality, actually arises naturally when studying certain problems in statistical mechanics, maybe modeling the energy states of particles or configurations of a system, perhaps. It shows that these abstract number patterns aren't always just abstract. They can be the language describing physical reality. It's quite profound, really.
Wow. So these numbers, 3, 14, 39, might actually relate to how physical systems behave.
Potentially, yes. Or at least the mathematical framework developed to study one sheds light on the other. The OEIS entry even mentions there's an annotated scanned copy available, which is fantastic for historical research.
That's incredible. Finding physics in a number sequence. And the OEIS entry also has sections like cross-refs and adjacent sequences. What are those for?
Think of it like a map or maybe like related articles on a website. The cross-refs point to other OEIS sequences that are mathematically related to A000263 in some specific way. Adjacent sequences just shows you the sequences immediately before and after it in the OEIS numerical order, which can sometimes spark ideas or show nearby families of sequences. It helps you see that A000263 isn't isolated. It's part of this huge web of mathematical ideas cataloged in the OEIS.
It's like exploring a mathematical neighborhood.
Precisely. And finally, there's the keyword non. Short for non-negative. It's just a tag confirming that all the terms in this sequence, AN, are 0 or positive integers, which makes sense as it's a count.
Right, you can't have a negative number of solutions.
Exactly. It's another small piece of classification data.
Okay, so let's pull this together for the listener. We started with this sequence, A000263, with a slightly intimidating name, but we've seen it's actually about something quite concrete. Counting pairs of distinct positive integers by 1 by 2, where squart by 1 plus squart by 2 is less than or equal to n.
We saw how that definition leads to the sequence terms, like A33.
And we looked at how algorithms can compute these terms efficiently, translating the math into code.
Yeah, using those clever counting tricks.
Then we touched on its history, Sloan's foundational work, and that amazing connection to a 1951 paper on statistical mechanics.
Showing these things don't exist in a vacuum.
So for you, as someone exploring these ideas, what's the takeaway? Why does diving into one sequence like this matter?
Well, I think it shows a few things. First, how Relatively simple rules or constraints like that, inequality and the conditions on by 1 by 2, can generate complex and interesting patterns. The sequence grows quite fast. It's not immediately obvious what the formula might be.
Or it's not trivial.
Second, it highlights the elegance of mathematical definition, being really precise about what you're counting, and how that precision allows you to then build algorithms to actually do the counting. And maybe most importantly, it's about seeing the structure and, dare I say, beauty in numbers, and appreciating that this structure often reflects something deeper, maybe even about the physical world, like that statistical mechanics link suggests.
Finding order, finding connections. It's not just about the numbers themselves, but what they represent and how they link together.
Exactly.
So here's a final thought to leave you with, something to maybe mull over. We saw the sequence 000663 has the surprising link to statistical mechanics through that Agarwala and Aulick paper. It makes you wonder, what other connections are lurking in the OEIS? Could some other sequence, maybe one that looks even more obscure, actually hold the key to understanding some other scientific puzzle or some pattern in finance or biology or who knows what?
The tantalizing thought, isn't it?
How could you use the OEIS not just as a lookup table, but as a tool for discovery, for finding those unexpected bridges between different fields of knowledge?
The potential is vast. The OEIS really is more than a list. It's a map of mathematical connections, many still waiting to be fully explored.
A great place to let your curiosity run wild. And on that note, we'll wrap up this deep dive. Thanks for joining us today. Until next time, keep exploring, keep asking questions. There's always more to discover.